Okay, so welcome back to the live session again. So again, we will discuss some of the problems. Okay, so let me share my screen. Yeah, I hope that screen is visible.
Yes.
Okay.
Yes.
Yeah, so I might be repeating some of the questions which I feel like those are important one that should be discussed maybe once or twice. Okay, so as you can see, question one is we will first recall some result, and based on that result, we will try to solve some question. So it says that if you have a subfield of C and fx be a polynomial which is an fx, so and let's say degree of f is n, and d is the discriminant of, which of course we know that it is not in the, it appears to be in the extension, but later it can be proved that it is actually in the base field also if you have some extension. So d be the discriminant of f and delta equal to root d is in k, where k is over f is a some discriminant, some extension of f. Then if delta is in f, then g is in an, and if delta is not in f, then g is not contained in a. So that means it depends whether delta is a square or square free element on the base field. Okay, so I think this should be in K, I guess. Let me write first in D is in K. And K over F be an extension, field extension. Okay, now we know such situation. Now let's go to question one. Part A says that what are the possible transitive subgroups of S3? Huh?
So transitive means given any two indices I and j, there must be a sigma in S3, sigma of I equal to j or sigma of j equal to
Well, okay, let me rewrite. I think sigma should be not in S3, but the subgroup which you are talking. So let me write. So for me, my H is a subgroup of G, and G for me, G is S3. And we are looking that when we say H is transitive, so by definition, so of course we know that symmetric group of S3 is nothing but all bijections from a set of three symbols to set of three symbols. Usually we take it 1, 2, 3. So of course we know that since sigma is a bijection, of course we know that given any ij, sigma always maps some I to j, right? This is because of set of all bijections. It's all bijections. And all bijections will cover all the possibilities of sigmas which can map I to j. So it is all about H mapping that I or j. That means given any two indices I and j, we say H is transitive if there exists a sigma in H, not in G. G we know anyway there, such that sigma I equal to j. Yeah, so right, this should be in H, right? Not in S3. So this is the definition saying that then we say that H is transitive subgroup of S3. Right. Now let's look at the subgroup S3 closely, and I think we will be able to say something. So we of course know there are two, that always a one n cycle, Sn n cycle, and a two cycle always generate the group. This we know, but we can expand the group itself because this is a smaller order group. We can read all elements. Yeah, so looking at the structure, it's always easy. Now we can see how many subgroups possibly we had. All subgroups. Yeah.
all subgroups. Identity alone is a subgroup.
Okay, this is one subgroup, yes.
Then E comma 1 2 is a subgroup. E comma 1 2, E comma 1 3, E comma 2 3. Then E comma 1 2 3,
E
1
comma
3
1.
2, 1 2 3 1.
All right. And S3 itself.
Yes.
Right. So we are just checking among this list. We don't have many elements because this is a small group where we can see all possible subgroups. Yeah. So if you can see clearly, you can tell me which subgroup give me transitive property and which does not give, right? It's very easy to see the structure. So clearly, if I say I and j, any ij, where ij is not equal to identity, it's clear that there is no such permutation because identity means it fixes all. So it fixes 1 to 1, 2 to 2, 3 to 3. That is the only bijection we have inside H1. So there is no such sigma which can map any non-identity elements, right? So clearly H1 cannot be such transitive, right? So can you argue something about H2, H3, H4, 5?
H5.
H5, what is that?
You mean to say all of them are transitive subgroups?
All H2, H3, H4. Is that you are saying?
I think H5 is a transitive subgroup.
Okay, this is you think that is transitive. Okay, what about others? I think it's not that difficult. Just look at any two elements. Can you find the bijection which maps the two distinct elements that you choose? Can you find that?
1 2 I take.
Okay, 1, 2 you take, 1 and 2 you take, and which group you are taking?
H4.
H4, all right. Then do you have any sigma from 1, 2, 3 to 1, 2, 3?
No.
Which maps 1, 2, 2? No, right? Same for H3. The same pair will work for H3, right? And in this pair of I and J, you choose this to be I, this to be J. That will serve the purpose for H2 in order to say that H2, H3, H4 all are not transitive. Is okay, right? So therefore, the only possibility of being transitive subgroup is H5 or S3. H5 is also a known group. Can you identify H5 with some group which you know?
Or S3, right? H5 or S3?
Yes, H5 and S3 both are transitive. So I'm just asking, can you identify H5 with some group which you know already? I mean, this group has some name.
I don't follow what you are asking.
Okay. I'm saying that this H5 is some group which we, just like S3, we have a name for this group, order 6 elements. Same thing, we have H5, which is E123, 132. The same as you can write E, 1312, 1213. And if you realize these are even permutations, so this is a group of even permutation. Now, can you see which group is this? This is A3, right?
Of even permutations. A3.
Yeah. So therefore, the only transitive subgroup of S3 is A3 and S3. Okay. All right. So now we have part B, which asks that if you have a polynomial over Qx, which is x cubed minus 3x plus 1, so is the G, by mean G is the Galois group of F. So here this is the meaning of G. So given this G, we are asking, is it a subset of A3 or it's a subset of S3? I mean, is it contained inside, is the Galois group for this F, is it contained in a A3 or not contained? Can we say something about this? Yeah, so first of all, let's recall the definition of Galois group of a polynomial. What is that? So here, what is the meaning of this G, which I'm writing to be Galois F? Yeah.
Galois F is Galois KF.
Galois K over Q, where K is?
K is the splitting field of the polynomial F.
Yeah, right. Okay, but if you see just by going the definition, looking at the definition, that you have to find the splitting field. That means you have to find the roots, right? And it's not always easy to get the roots, not always easy. So there is another way to see how a Galois group of a 3-degree polynomial, maybe specifically of the type that we have taken, is it contained in A3 or not? I think it is dependent on certain condition on something. And this is how we have written a recall in the above statement. So we are trying to say that if something Galois group of some polynomial is contained in An or not, that is being determined by some condition on D, right? So if that is the case, we can try finding D, right? And I think D can give many information about the group of the this polynomial F, Galois group, right? But definition of discriminant, what is that? Can you recall once that also?
That one, delta in F or delta not in F, we'll have to find out. So to
Right.
find delta, we'll have to find out what is the D.
D. And what is the definition for finding D? Yeah.
For a 3rd-degree polynomial, they were given a formula to find D.
Ah, okay.
Minus
So,
27, 4 coefficients with.
okay. Can you write some general statement? Can you tell me some statement about any F that when F looks like this, then you know the discriminant of the F. Yeah.
Minus 4a cubed minus 27b squared.
Okay. What is A and what is B?
That coefficient of x is a and constant term is b, and the coefficient of x squared must be 0.
Okay. And
For
is this
such
what you are talking?
polynomials, discriminant is given by
Yeah.
minus 4a cubed minus 27b squared.
This is what you are trying to say?
Yes, minus 4a cubed minus 27b squared.
All right.
Our cubing a is minus 3.
For our case, A is minus 3, right?
B equal to 1.
So B,
Implies b is equal to minus
just
4 into minus 27.
Just a moment, just a moment.
Minus 27 into 1 squared, which is 3 times 27 is 81. So delta equal to 9.
This is what the discriminant is, right?
Yes.
All right, so it is a square. Then let's go back to the result. What the result says? Suppose
So
we got the
delta
square.
belongs to F.
Delta belongs to F, yes.
F
Then
is
in
our
that
Q now here. Huh?
F is F, for us it is Q, exactly right. Then
So delta belongs to Q and means G is contained in A3.
exactly. So therefore, our Galois group is contained in That's right. Can you tell something about now equality? Is the group equals to A3 or just contained in A3? Yeah. Can you say something about that?
A3 consisting of 12 elements.
A3, no.
S3 is 6 elements, so A3 3 elements.
Yeah. So A3 has 3 elements. Exactly. Now
we can find the dimension of K over Q. Or
okay. So Galois group has. So if Galois group has contained in A3 implies this, it is either less or equal to 3. Do you agree this? From this we can write this, right? Hello? Hello?
yes.
So
the question is, we have to find whether equality occurs or not.
yeah.
We need to find what is our K and then find the dimension of K over F.
Well, I'm saying that there is no need. If you can think more carefully, then there is no point in looking for the splitting field, because usually finding splitting field for any arbitrary polynomial is not that easy. Not that easy. Okay, so let me just tell you one thing. There is a hint that I'm trying to give you. So if suppose you have some group whose order is less than equals to 3. And what is the possibility of that order? Either order is 1.
Either 1 or 3.
Why not 2? Why not 2?
Alpha F is a subgroup of A3 which consists of 3.
Yeah, exactly. So of course it cannot be, because your Galois group order should divide the order of 3. In fact, your Galois group of F divides 3, not just less than equals to 3, but divides 3. And therefore you have either 1 or 3. You have to just claim that it cannot be 1. So when do you feel that the degree will be 1? So if your Galois group of F, yeah.
Consisting only identity.
Yes, your Galois group is just identity, but what is the meaning? That so Galois group of F means that is the Galois group of splitting field of F over Q.
So splitting field is F itself.
Is Q itself.
Q itself here.
Exactly. But
here,
can you? Yeah.
Here all roots, I think, are not in Q.
Well, you can say one thing, that this polynomial is irreducible. As long as you say that, are you done? Because if splitting field is Q, that means all the roots are in Q, right? And if I can say that the polynomial is not reducible, that means it is irreducible.
It is
Then,
irreducible.
yeah, if we can prove that, then that will be okay, right?
Yes.
Yeah, so therefore, once we can prove, so claim, therefore, if we can claim that F is irreducible, then therefore, splitting field of F cannot be Q. And therefore, your order of the Galois group cannot be 1 at the same moment. It cannot be 1. And therefore, it has to be A3 only. So now finally, the only thing remaining is to check whether this polynomial is irreducible or not. Now, since we are working over polynomial over Q, now how many tests do you know in order to check a polynomial is irreducible? Yeah.
Einstein criterion,
Eisenstein criteria. Can you apply that?
Cannot apply here.
That will not be applied.
If we replace x by x plus 1.
Okay, let's replace x equals by 1 then.
Or we can find the rational root test.
Okay, rational root test. Let's look this way. Anyway, you have just told me, so I'm trying to write it now. So it is this.
So not possible.
Again, you are not able to write this. Maybe some other substitution will work. But as you said, let's look at the root test, rational root test. Can you tell me what is that?
That we have to consider a naught and an.
A naught and an. Well, okay. For us, this is the polynomial x cube minus 3x
so
plus 1.
an is 1, a naught is also 1.
A naught is 1. And for us, an means a3 is 1, right?
R should R by S is a root provided R divides A3.
R by S. If and only if. What divides what?
R divides A3.
A naught, right?
R divides
A naught, right?
A naught. A3. Your A naught is a last term?
For me, A naught is the last term, yes.
Okay.
Sorry,
R divides the last term, right?
Okay. Mm-hmm.
Here both are equal. Okay. S divides also 1.
Okay. A3.
The possibilities are R equal to plus or minus 1. S is equal to plus or minus 1. Yes, not R. They have repeated R twice.
Sorry. Okay. And it's easy to check, right? Which are the like possibilities?
So
which
R by S is 1 or minus 1.
Yeah.
Both are not roots of x cubed minus 3x plus 1.
Exactly. And therefore, okay, both these choices do not give zeros of x cubed minus 3x plus 1. And therefore, by rational root test, f has, can I say f is directly reducible? Just having no root, is that enough? Yeah.
I think it is not enough.
No, it will be enough because we are working in degree 3, I guess.
We are working in?
Degree 3.
Oh, degree 3.
Yeah, I think it should buy, because if your fx is degree 3, then gx into hx, either this is degree 1 or this is degree 2 or this is degree 2. This is degree 1. But in either case, degree 1, that means there should be a root. As long as you are splitting your polynomial, either in degree 1, 2, or you can split in degree 3, 3 polynomials, 1, 2, 3. But in either case, you should have a root. So degree 1 means you have a root. And that we have anyway seen that there is no root in it. So therefore, degree 3, it's enough to say that it does not have root. But more than 3, you have to say something else also. There can be two quadratic polynomials. But that situation does not apply for degree 3. This is okay, right? All right, so therefore this is irreducible, and as long as we know it is irreducible, its Galois group is exactly A3. So therefore we can say that Galois group of F is exactly A3. All right. Now let's going back to the, okay, so we have another polynomial, part C, where we have x cube plus 3x plus 1. So what is the Galois group of this polynomial? Yeah, how do you find that?
Same method.
Same method, right? So
Yes.
it's just enough to check what is the discriminant, the same thing, and then we know that in this case, now we know that how to find. Yeah, so I will leave this case. Let's go to question 2. We have a finite extension K over F. So part A says describe the resolvent cubic for a degree for polynomial f in fx, where fx is contained in, where f is contained in C and degree of f is 4. Now, what is the resolvent kernel?
It is x minus beta 1, x minus beta 2, etc.
Okay, let me write. So resolvent
Where beta
cubic.
1, beta 2 are calculated using roots alpha 1, alpha 2, etc.
Okay. So first of all, in order to describe that, we have to know the roots. And we are not restricting ourselves roots to f, let's say. They can be like anywhere, any.
We have taken degree 4.
Yes, I am taking degree 4.
Okay, we can take it alpha 1, alpha 2, alpha 3, alpha 4.
Yeah, so let alpha 1, alpha 2. These lie in some splitting field of f, yes.
Yes, then beta 1 is
Beta 1
equal to alpha 1, alpha 2 plus alpha 3, alpha 4.
Mhm.
Beta 2 is alpha 1, alpha 3
Mhm.
plus alpha 2, alpha 4. Beta 3 is alpha 1, alpha 4 plus alpha 2, alpha 3.
Okay, so there is some nice structure about this resolvent cubic. What is that? So you define resolvent cubic by G, and what is that?
X minus beta 1, x minus beta 2, x minus beta 3.
This is the polynomial. In general, it looks like this polynomial is in, I think, in Kx, where let's say K is the splitting field of F over K over F. Sorry. So where all root lies, there the sum also lies, and therefore their beta is also lies, and therefore polynomial looks like is in the splitting field. But there is an important observation that this Gx is actually is in Fx base field, not just in extension field. I think that is pretty simple. We will not discuss, or if we can discuss, then it's a simple thing because sigma Gx is same as Gx for all sigma in Galois automorphisms of K over F, let's say. Okay, so therefore this polynomial is actually in Fx, and now we are trying to look at, so definition is clear, I think, what is resolvent cubic. But this resolvent cubic helps us to determine the Galois group of a 4-degree polynomial. So there is statement which I'm trying to recall here. So this is a recall. So this is a recall that if you have any irreducible polynomial of degree 4 and D is the discriminant, G is the resolvent cubic, and K is the splitting field. So given this K is the splitting field, and look at the Galois group. Now, this Galois group is being determined by two facts. One is how the discriminant looks like. Is it square or not square? But even D square, if you have D square, then there are two possibilities, and here we have three possibilities. But that also get clear once you know the resolvent cubic, and if your resolvent cubic is reducible and D is a square, then you have only one possibility of Galois group. And for irreducible, for D being square, unique choice. D being non-square, again unique choice. But here we don't know the choice. Here there are two choices. But based on the degree of extension, they are also clear because one has degree 8, one has degree 4. All right, so I think this table itself distinguishes all the possible things about a degree 4 polynomial. Okay, now suppose we understand this, right? Question is find the Galois group of the polynomial x power 4 plus 2x minus 2 over qx. Okay, how will you approach, let's say?
So we have to find D and also have to find G. Then only we can refer the table.
Exactly right. So as you said, we can refer to the table only. We can, provided we can find D and we can find the G. Okay, so I think that for such polynomials, I think as you said about degree 3 polynomial, something is known, right? Can you just look into the notes and tell me how to find, let's say, D and how to find, let's say, G?
So we need to find the roots.
Hmm? Yeah, but as we saw the previous example, x cubed minus 3x plus 1, we did not bother about looking at the roots, right?
So we consider x power 4 plus 2x.
Hmm?
Or something to do with the number of non-real roots.
Something to do with number of non-real roots. Well, yes, we can think about that also, correct? But for time being, I think it's important that how to find this D.
Okay.
And D for D, I think as you told me, there is some formula, as you told about degree 3 polynomial of certain form.
So
You
for
could
3
tell
degree
some.
we have a formula, right?
Yes, for degree 4 also we have a formula.
There is a formula.
Yes, you're right. So can we make use of that here?
3, 4, minus 27 minus 27 C cube. Coefficients are 256 and 27 will come.
Okay, let me also check whether. Okay, so let me just write. If you have x power 4, let me just write. So in general, so suppose your polynomial fx is x power 4 plus cx plus d, let's say. Then discriminant, I think it's given in, as sir mentioned in the lectures, that it is well known in, if you see in some literature or online notes, you will find this thing. Yeah. So here for us, what is the polynomial? So for us, polynomial fx is x power 4 plus 2x minus 2. All right. And not just that we can find the discriminant. In fact, there is something else or also known, resolvent cubic is also known. So resolvent cubic of f is also known for this, and that is x power 3 minus 4 dx and minus c square. I think if you see the notes, you will find this. All right, so since we know this, so for us the polynomial is this, and now can you quickly tell me what is the discriminant of f following through the formula and resolvent cubic of f?
So for fourth degree also we call it as resolvent cubic.
No, for 4 degree only, no. So this resolvent degree was only for 4 degree, right?
Okay. Yeah. So there are beta 1, beta 2, beta 3.
Right. So as you know, finding roots is not that easy. Therefore, people discovered this formula. All right. So discriminant, as you see from the formula. So can you see quickly for our example, what are the discriminant and resolvent cubic?
Okay, discriminant 256
256
into 1 cubed, okay, minus
minus 2
256
cube.
minus 27 into
C power 4, right? Now this is
You can
Nothing
take
but
2
what
power
is this
4
power?
this 2
Yeah,
power
2 power 4.
8.
Okay, 2 power 8. Yeah, I think so. 2 power 8, 5, 1, 2, 1, 0, 2, 4. Yes.
So minus 128.
Okay.
Then followed by minus 27.
Okay. And that seems to be, it's a negative, right? Minus 2 power 4 times some number. I think you can write it 128 plus 27 is 155. Now, easily you can see this is a negative number. So as soon as you have, so can you say something about the discriminant, whether it is a square or non-square? Yeah, because we have to determine. So table says that you need D to be square or non-square. Now we have something D. So this is our D. So this is nothing but D of F, discriminant. So as long as it's negative, can you say something about that? Is negative a square element inside Q? Is this a,
not a square?
this? No. So since minus 1 is not a square, no. Answer is no. And in general, any negative number will not be a square element. Therefore, D of F, once you have it is negative, then clearly D is non-square in Q. Square in Q. Right. So at least where we are in this situation now. So we are in this situation that D is non-square. Now we have several possibilities of having been our Galois group. Either it is D4 or C4 or S4. Yeah, which one is this? Can you say something?
We have to find now G.
Yeah, even G is also given, right? Even G we know from the formula. So what is that, G?
G of x equal to x cubed minus.
Okay, let me write resolve.
X cubed plus 8x.
X cubed minus 4dd is minus 2. So therefore plus 8x, yes. Minus c square.
Minus c squared 4.
So minus 4. All right. Now we have to check the irreducibility or reducibility for this. I think that should not be very difficult, right?
As it is Einstein criterion.
Eisenstein criterion. Okay. So what substitution or what thing will you use here? Well, clearly you can see that 2 divides 8 and 2 square also divide 4, right? Or minus 4. So Eisenstein criteria says as long as you can find it. Sorry.
So the first two terms you can take x common. Okay. X squared plus.
That should not give anything, I think.
So rational root test shall we try?
Okay, let's try for rational root test. What is that? Let's say R by S. Then this is the root for above polynomial if R divides
minus 4.
A not. Yes, and S divides 1.
S divides 1.
So what is the possibility for R?
So here R is equal to 1 minus 1, 2 minus 2, 4 minus.
S is 1.
S is equal to plus or minus.
S has to be 1, right? Well, it depends at which, I think maybe it depends at. No, but I think S is 1, right?
Why not minus 1?
Okay, so is minus 1 divides 1? I think, yeah. Sorry. Minus 1 times 1. Sorry. Plus
No,
minus
not
1.
plus or minus.
Right. Sorry. It should be plus minus
Therefore,
1.
R by S possible values 1
Hmm.
minus 1,
Hmm.
2 minus 2, 4 minus 4.
Yeah. So can we see that? First of all, is 1 is the root? No, right?
1 is not a root.
Minus 1?
Not a root.
2?
2 we can check 2 cubed minus 2 cubed, no.
Minus
2
2
also
cube
is not coming. 60.
plus
So none
4?
of them is a root.
Yeah. So therefore it is irreducible. And therefore you can quickly say that what is the group?
A root. Now this
Sorry?
is irreducible as well as so S4 is the only possibility.
Yeah, for this S4 is only possible. Yes. Okay, just give me a minute. Okay. So I have to mute for a while. I'm sorry. How do I mute? Yeah. Sorry, I had to attend some call. Yeah. Okay. So we were at the finding the group. I think for this part, the Galva group is S4. This is clear, right? So I think if it comes that the polynomial comes out to be of certain form, which you, let's say you, just like we have x power 4 plus cx plus d of that form, then quickly you can find the discriminant through some formula and the resolvent kernel. As long as it's a degree 3, because you know that resolvent cubic, sorry, that has to be a degree 3 polynomial because you have x minus beta 1, x minus beta 2, x minus beta 3. So product will be a degree 3 polynomial. And as long as you are in degree 3, it's very easy to check the irreducibility either by Eisenstein criteria or by, let's say, um, this rational root test criteria. So I think then it's simple to say what is the Galois group. All right, so what is the Galois group for the other polynomial? I think this is more easier. X power 4 minus 2.
I think the same is here you have C value 0.
C value 0. Okay, then
C value 0 means we can easily calculate C0 means it is 256 d cubed. I think it is a square.
256. It will be, well, it will be negative, right?
Minus 2 cubed.
Hmm.
So
As
it
long as
is,
you are, yeah,
so
as
D
long
is
as
not a square.
D is not a square, of course, then again you are in the same situation. But what about the resolvent cubic?
This resolvent cubic is x cube plus 8x.
Okay, let me write. So resolvent cubic 4x power 4 minus 2 is what you said, x cube minus 8x. And discriminant is what you said, I guess, minus 2 power 8, which is negative and therefore not a square. So what can you say about the resolvent cubic?
Resolvent cubic is reducible.
It's reducible. So as long as you are reducible and the D non-square, I think you will fall in this category that either your group is D4 or is C4. Now you are not sure. So now our Galois group of F, which is Galois group of x power 4 minus 2, this is either D4 or C4. One has to argue now which one of these. Can you see that?
So C4 has 4 elements and D4 has 8 elements.
Yeah, there is a difference. Yeah, but then how to distinguish which group is that which we are looking for?
So this is F is 4th degree. Is it
Yeah. So I think it's very easy because sometimes we can use a definition also. So for this is nothing but the Galois group of L over Q, where L is the splitting field. Splitting field of F x power 4 minus 2 over Q. So can you tell me what is that L? I guess I think you can tell it, and quickly then you can tell what is the group.
So this L over x power 4 minus 2 is irreducible over Q.
This is irreducible over Q. Okay,
Therefore,
I agree.
L over Q is equal to 4.
Well, if you say this, then I will not agree. If I give you a simple example, x cube minus 2, this is irreducible over Q, right?
Yes.
What is the degree of the splitting field for this polynomial? Yeah, if I ask you Galois group of L over Q, where L is the splitting field of x cube minus 2, what is that?
This is 2. Degree 2.
Degree 6, right? Why? Because the splitting field is Q 2 power 1 by 3 comma I. Right? Because its roots are 2 power 1 by 3, 2 power 1 by 3 omega, and 2 power 1 by 3 omega square. So splitting field has to be this. But this is degree 3 and this is degree 2, so it's degree 6. So, well, as long as you have polynomial degree 3, its possibility is 3 factorial. We cannot say always 3, but it is 3 factorial.
Less than or equal to 3 factorial.
Yeah, less than or equals to 3 factorial. That's okay. Now, knowing all these facts, let's go into the above question. Our question is this fact that x power 4 minus 2, what is the splitting field? It's not that difficult, right? We have done several such type of questions.
So let us write out the roots and then.
Yeah. What are the roots?
The roots are 2 power 1 by 4 minus 2 power 1 by 4. 2 power 1 by 4i minus 2 power 1 by 4i.
Okay, as long as you know what is the splitting field, then can you write the splitting field L as?
2 power 1 by 4, 2 power 1 by 4 comma I.
Yeah, and what is the degree?
This is 8.
This is 8, not 4. Yeah. All right. So this is 4, this is 2. And I think my pen is not working. This is 2, therefore
So
this
conclusion,
is 8.
the conclusion is D4.
The conclusion is D4, exactly right. So finally, this is the group. So sometimes not just that the resolvent kernels or cubics and discriminants are going to help. Sometimes your basic definition also help. So for this group, this is D4. All right. So I think we are done with this question. Let's go to question number 3. So when do we say a group is solvable?
So group solvable means there must be a tower of subgroups
Tower of subgroups, okay. What's that?
That smaller one is a normal subgroup of the previous one.
Smaller one are normal subgroups of the bigger one, yes. Okay, let me write. I think it will be easier for you to say. So we should have a finite chain. So the precise definition is that for a G to be solvable, there exists a finite chain of, or tower of, as you can say, but it's okay, subgroups GIs of J such that, so once you writing the group, let's say G0 containing G1, so on, containing Gn is equal to G, such that this happens where all your GIs are normal in GI plus 1. This is true for all I from 0 to n minus 1. And one more thing, what is that? There's one more condition. Yeah, then other than normality, there is one more condition, right?
We say that when element is solvable, we say alpha belongs to G.
Well, group to be solvable, right? Not the element, right? I think you are confused with the definition of element being solvable by radicals. So we have a composition series. We always you say, I think composition series maybe. Where so you have a chain of subgroups such that all previous subgroups are normal in the coming subgroups, and the quotients are abelian, right? Yes, abelian for all I. So if such a group, you can construct any one chain. We are not saying how many chains you can. If you can construct one single chain for the given group with this property, then you can always say the group is solvable. And if you cannot find a single chain for the group, then you cannot say whether that, I mean, you cannot say that is solvable. That has to be not. All right, so we understand the definition. So can you give quickly some examples of solvable and non-solvable groups? Solvable means you should find a chain of normal subgroups. And if you cannot find, then they are not solvable. Of course, saying non-solvable is tough because you have to argue there is no such chain. But saying solvable is easy. You have to find one chain. Okay, if I ask you, let's say a group of order 2.
S3, A3.
A3, S3, okay. What about S2? What about S1?
S1 consisting only the identity, right?
Yeah, then that's trivially solvable, right? So S1 is trivially solvable, yes. About S2?
In S2, you have only two elements, identity and 1, 2, 1, 2.
Okay, then what is the subgroup possible?
Therefore, this is identity contained in S2.
Identity contained in S2. Okay, this is the chain we have, right? So can you argue about this chain? Is identity a normal subgroup of S2?
identity is not a normal sigma.
The normal.
It is normal. Okay.
It is normal, yeah.
Yes,
if you take G inverse.
Inverse is nothing but E.
Yeah. All right, so therefore this is trivially normal subgroup and therefore you don't have to check this. But you should have to check one more condition, that the quotient has to be abelian group. Is that also true?
So the quotient is S2 itself.
Yeah, yeah.
It consists of two elements, therefore they commute.
Okay, yes, you can say that way, or you can.
So S2 in fact is cyclic, therefore
abelian. Yeah. This is more good logic, that is cyclic, therefore abelian, therefore it's clearly solvable. What about S3?
S3 is not solvable.
S3, is it non-solvable? Okay, why? Can you prove that? I told you, proving something is non-solvable is hard. Maybe you can quickly check whether there is some such a chain of normal subgroups or not. So if you can see S3, so which subgroup you can always say that is normal. In a group, which subgroup you can always say that is always a normal subgroup for any general finite group. Do you know some idea? Do you remember some result?
A3 is normal.
Why?
A3 is normal. You can make A3 as the kernel of homomorphism.
Kernel of which map? So let's define.
The map takes identity, the odd permutations to 1 and odd permutations to -1 and even permutation to +1. So this is easily we can check it is a group homomorphism.
Yes.
Kernel pi is equal to that set of all even permutations, that is A3.
Indeed.
Kernel of a group homomorphism is a normal subgroup.
Indeed.
So A3 is normal.
Yeah, exactly. There is one more criteria. Index to subgroup is always normal subgroup, right?
Index is 2.
Index is 2. So yes, this is one more way. Now, knowing this normal subgroup, and you can also know A3 has order 3. So any subgroup which is contained in A3 has to be identity only, right? You agree? Because it is a prime order subgroup. So any subgroup which is contained in A3, that should divide the order of A3. But order of A3 is 3. Therefore, any subgroup which is contained in A3 is either order 1 or order 3. Therefore, non-trivial group has to be identity only. Understand? So the only possible chain we have this. Do you agree?
But in fact, these are the only 3 normal subgroups of this 3.
That's also true. That's also true. So yeah, either way you can say. All right, so then this is the only possible chain of normal subgroups in S3. Now there is this and one more criteria you have to check in order to say it is solvable, right?
Abelian nature.
Abelian nature. So what can you say quotient S3 by A3? And what can you say quotient A3 by E?
A3 by E
is A3.
A3 by E is same as A3.
And
A3 is not really.
What is the order of A3?
Order of A3 is 3 cyclic abelian.
Yeah, this is cyclic abelian. What about this? What is the index?
Index to abelian.
Cyclic. And therefore, finally, what is the statement about S3? Is it solvable or not?
It is solvable.
It is solvable. All right, so let's go to, I mean, there are several examples. If you want to discuss, we can discuss S4 also. Yeah. Is it solvable or not? So let's look at first of all the normal subgroups. As we know that what are the properties of checking normal subgroup is looking at the either by your way finding the kernel of that trivial homomorphism that you are taking. That means sign homomorphism. Sign of, if your permutation is odd, then -1. If it is even, then you take +1. So it is the sign of permutation, and that the usual homomorphism, and therefore kernel is nothing but A4. So therefore, you know that A4 is one normal subgroup of S4. In other ways, the index of S4 is 2, A4 is 2, and therefore A4 is a normal subgroup. Either way, you know this thing. Now, A4 has, so S4 has cardinality 24, A4 has cardinality 12. So A4 is still a big group. It can have several subgroups, which is normal. Can you find one normal subgroup inside that? Okay, so you can check that this Klein 4 group is actually a normal subgroup. Sorry. So, or sometimes people write it as V4, sometimes people write it as Z2 pro Z2. The same thing, this is one group which we are saying, this is Klein 4 group. All right, so it's a normal subgroup of A4. This you can check. Then therefore we have P contained in K4 contained in A4 contained in S4. This is a chain. At least we have a chain of normal subgroups. That this one thing needs to be checked. K4 is normal. This is the only thing that is remaining. Rest is, we know that they are normal. All right, so let's talk about the quotients. That is easy, I guess. Yeah, can you say about that quotient? That is easy.
K4
What about that?
K4 over E is K4.
And is it abelian?
Yes, it is abelian.
Yes, this is abelian.
Hence, 4 group is abelian.
Yeah, correct. What about A4 by K4? What is the index?
K4 consisting 4, that is 4 factorial is K4 12, index is 2.
This is 3, right?
3.
This is Z3, which is a cyclic group, and therefore abelian.
Abelian.
What about S4 by A4? That is also easy, I guess.
That is index is 2.
Yes, that is also cyclic abelian. And so finally, the upshot is all SIs are solvable. But this is not the way we write. Sn are solvable for all n 1, 2, 3, 4. All right, so maybe we can see later, but the one example of non-solvable is Sn. In fact, all n greater than 5 are not solvable. All right, so we will discuss maybe this thing later, why S5 not solvable. Let's go to question number part 3. State the theorem by Galois which gives equivalence to prove a polynomial to be solvable. So, you know, polynomial being solvable means all its roots are solvable. And solvable means they are solvable by radicals. That means you have to find the tower of fields where our element is, or the roots are in the extension field that is a radical extension. Or root is lying in a cyclic extension. Or roots are lying in a abelian extension. This is the all equivalence we know about checking roots are solvable or polynomial being solvable. So, but there is one theorem that that is a celebrated theorem by Galois, which says that you can look the structure of, polynomial structure being solvable or not through Galois group. Huh? Something
So
with the Galois group.
F is solvable if and only if Galois F is solvable.
Exactly. So I think this is the most beautiful results of Galois. So polynomial F is solvable. Is solvable if and only if its Galois group is solvable. And since we know that we know S1, S2, S3, S5, S4, sorry, whenever we can have the Galois group of a polynomial being one of these, then we are so sure that polynomial is solvable without checking its roots are solvable by radicals or not. So of course, this is very nice and beautiful result. All right, so let's go to question 4. Let's suppose we have a polynomial of Qx of degree n. Can we justify this fact that polynomial is irreducible if and only if Galois group is a transitive subgroup of Sn? Yes. So we have been using this result, but somehow I find it more very interesting. The proof is quite interesting, so I felt like it should be discussed again. So I think one way is not that difficult. So suppose we know the roots. Let's say we know f is irreducible. Okay. Suppose we assume f is irreducible, and suppose it has some roots. And using irreducibility, we can say the roots are all distinct. Can you say that? Huh? So I'm saying that given f, let's say given f is irreducible, and suppose alpha and beta with they are some roots, they are roots of f. Can they be equal? Huh? So suppose if f has repeated roots, then your polynomial should be written like this, right? Can you use this fact, the description of f, to say that is that possible or not when you have f is irreducible? No, right? Because your f prime will be then x minus alpha times some factor. Then f and f prime have some same factor, right? But for irreducibility, f, yeah, so that is not allowed. So once you have a irreducible polynomial, it cannot have repeated root. All roots will be distinct. This is one beautiful thing that one has to observe. All right, so all roots are distinct. Assuming that this, you know that we have seen that if you attach one root to your base field and one root, other root to your base field, can you say something about are they isomorphic or not? Hmm? So just like x cube minus 2, this is irreducible over a q. Let's look at example. And if I try to attach one root and attach another distinct root, are these two fields isomorphic? Yeah, can you say something? So that means you can define, can you define isomorphism phi from q2 power 1 by 3 to q2 power 1 by 3 omega? That means you have to define phi 1 1 onto and homomorphism. Can you do that? Where will you map q to? Q elements, where will you map?
Q is of the form a plus b times 2 root 2 power 1 by 3.
Okay. Okay. It's all about finding where will you map. These are elements of Q. It's all about where will you map to Q. Q has to map to Q, right? So then Q has to
a
be
plus b.
Yeah, it all. Yeah, so where will you map 2 power 1 by 3? This is all about mapping 2 power 1 by 3. Where are you wanting? You want to be in that field. Where will you want to? Where will you map this element 2 power 1 by 3? So of course, you know, root has to be mapped to root. That you know, right? So the root is nothing but 2 power 1 by 3 omega. So it's simply you can map it to 2 power 1 by 3 omega, right? That's it.
Yes.
Is it 1 1 on 2 homeomorphism? All the properties are satisfied. So once you attach a root of the same polynomial, as long as your polynomial is same, it's okay. Then you can map root to root, and you will have an automorphism. This is how we write the Galois automorphism, right? We map roots to roots. And of course, our base field is always fixed there, just like Q is being fixed here. So this is one consequence, and therefore they are always isomorphic. And not just that, whenever you have a splitting field, let's say K, right? So suppose we can extend this idea to all the roots. So K is, let's say, splitting field of your F. You can extend the same thing to there also, right? And therefore, if your G is nothing but Galois K over F, which is nothing but your Galois of your polynomial F, then it's very clear that given any roots, K to K, any roots, here it is roots, here it is roots, given any two roots, you can always find a sigma, right? Always find a sigma. Because your all automorphisms are nothing but permutation of roots. You are permuting roots. One root is mapped to the root, one is to other root. And therefore, given any two roots, you can always find a sigma, right? Therefore, your Galois group is nothing but transitive subgroup, right? Transitive subgroup. But of which group? Since we know if F has degree n, then the splitting field is always n factorial. So that means your Galois group will always a subgroup of Sn. Once you have degree n, it is a subgroup of Sn. And therefore, this is a subgroup of Sn. The transitive subgroup of Sn. This is okay, right?
What is the definition of group is Galois K over F is a transitive subgroup.
All right. So we are trying to say that so here I'm trying to say that you can find sigma in this group, K over F, such that given any two roots of your F, that will be mapped by some sigma. So transitivity, let's check again. H is a subgroup of G. We say transitive if earlier it was Sn, right? Of course, even you can see your roots. You can form a list of roots, alpha 1, alpha 2, alpha n. And then 1, 2, 3, you can make it as a n symbols on Sn. And then you can somehow find a sigma, which will map your I to J. But I and J, nothing but they represent your sigma, alpha I, alpha J. I think there is a confusion with notation, because if you understand transitivity, you means the indices I and J, but somehow the indices are related with the roots. So as long as you have roots, you have indices, and therefore you have a permutation which maps roots to roots. That means there is a permutation which maps your indices to indices. So because you have listed your elements as some array, and array is depending on some, let's say, ij. So this is how you can connect the two things. All right, so therefore, whenever you have F irreducible, that you can always make sure that this is a splitting field. But why it's not, as we have seen earlier also, you can see in the our previous live session, that if your F is not irreducible, then this need not be a transitive subgroup, need not be. Because then some of the roots will be, that they'll be absorbed by Q itself, and you will no longer be permuting those roots. So some roots are gone once your polynomial is reducible, because that are lying inside Q, and that you cannot permute them because they have to be fixed somehow. And therefore you will lost the transitivity of the group. Okay. So one way is clear, that as long as your polynomial is irreducible, their splitting field has to be, the Galois group has to be a transitive subgroup. But suppose your Galois group is a transitive subgroup, can you say F is irreducible? I think that's also okay, because I'll write quickly because I still want to discuss some good questions. So suppose let your F is reducible. But you are assuming that Galois group is transitive subgroup. Or this is equal to Galois F. This is transitive subgroup of Sm. If degree of F is n. Suppose it is reducible, then we have F equal to G into H. As I told you, roots are always permute within the polynomial which we are choosing, okay? Suppose if I write you the polynomial x square plus 1, x cube minus 2. And if I try to write splitting field for this, you will say it is splitting field is nothing but, or maybe I will write this way, square minus x square plus 2. So splitting field is q root 2i. This is easy, right? To say that splitting field is this, sorry, x square minus 2. Now, if I ask you where will you map to and where will you map I, can you tell me where will you map to root 2? Under any automorphism sigma,
Plus or minus root.
plus minus root. And what about I?
Plus or minus I.
Why not root 2 maps to I? That is not allowed, right? Why? Because you want to make sure that root 2 is a root of polynomial x square minus 2 and it has to go to another root. But it should remain in the same polynomial. Polynomial you cannot change. Although your main polynomial is f, but it is product of two distinct polynomials and the roots of one polynomial will remain within its polynomial. It cannot cross the other polynomial. So therefore, if you take f to be reducible and you take f to be g into h, then roots, of course, you know, roots of f are several. Roots of f are same as roots of g, comma roots of h. So all roots of g and h together will give you the roots of f. But roots of h cannot be permuted by roots of g. Do you agree that? If you see in this polynomial f, your x square minus 2 roots are not permuted with x square plus 1 roots. That means you cannot map root 2 to I. Roots remain within the same polynomial. So if your f is reducible, then some roots of g will not be mapped to roots of h. But if group is transitive, then all roots of g should be mapping to roots of h by some element of Galois group. Do you agree?
Yes.
Therefore, once you have reducible, then such a possibility is not there that you can cover all the roots. That means some roots, in fact, roots of g and roots of h. There is no such sigma in Galois group such that root of g will map to root of h. There is no such. And therefore, it will contradict to the fact that Galois group is transitive. The assumption is reducible. This is wrong. Therefore, f has to be reducible. This is one beautiful fact that you cannot go outside your polynomial. I think it's clear, right?
Yes.
So let's go to question number 5. This is what I want to discuss more because this has been left in the exercise in the lecture series. Prove that subgroup of a solvable group is solvable. So let G is solvable. G be a solvable group. And H be a subgroup of G. The claim is H is solvable. I want you to first try. I think you will be able to try that given G solvable, how to prove that H is solvable. It's not that very difficult. Use the definition of solvability.
That is, there exists a chain of subgroups.
Exactly. So let's write. Given G is solvable, that implies that there exists a chain of subgroups GIs such that, yeah, chain of subgroups with what is the property on GIs?
Each GI is normally in GI plus 1 and GI plus 1 by GI is abelian.
This has to be true for all. Now I think with the examples, the theory is clear. All right. Now, given the facts about G, we want everything about H. Can you modify this chain? Simply, you have to modify this chain in order to get a chain for H. And that's very easy. Okay, given G, how to get H? I have to think about this chain. Think about H is a subgroup of G. Somehow
Which is subgroup of
G. So can you modify this whole chain? You have to modify with a single idea.
H is a subgroup of. So we need to find.
Instead of G, you need H. Can you change this thing so that it becomes H? Can you do something with G? Some operation.
So intersecting these subgroups with H.
Exactly right. Very nice. Very nice. So, as you know, H is a subgroup of G. G intersection H will be H only because H is a subset of G. Very nice. So as long as you have this, you can go to H intersection G1 containing H intersection G2. So on H intersection G, but H intersection G is H. Now this is chain, we know, of course, but you have to prove some properties that all the intersection parts are normal subgroup in one another and the quotients are abelian. Huh? So can you say about that? So you want to claim. So claim is H intersection GI is normal in H intersection GI plus 1. This is, I think, direct forward. And H intersection GI plus 1 by H intersection GI. This is abelian. I think first part is direct. Can you think of that? Well, you know something about, right? You know this property. You use here, huh? Then that is direct, right? So you have GI is normal in pen is not working. Huh. So we know that GI is normal in
G plus
1. Then if I intersect both the side with the same subgroup, it's still true, right? This is still true.
Okay, we can prove it by considering elements. Okay.
So this is very straightforward, that this is normal. This proof is about abelianness, yeah?
So we'll have to make use of GI plus 1 by GI is abelian.
Okay, this is given to you. Yes, of course. This is, of course, it has to be used somewhere. This is abelian. Yeah, you know that.
Whether we have to find some isomorphic copy of this H intersection GI plus 1 mod H intersection GI.
Now somehow, you know, here you have to use the group theory. So my hint is you have to use the fact there is a second isomorphism theorem for groups. First isomorphism theorem says just G by kernel is isomorphic to image of a file. given phi homomorphism between group. There is second isomorphism and third isomorphism theorem. I'm saying second one will give you something. So there is one observation, so let me do it. There is one observation that you can make. H intersection Gi, let's say plus 1. If you further intersects with Gi, what will you get?
Intersecting with GA, because GA plus 1 is a larger set. H intersection GA.
H intersection Gi only, right? Because your Gi is sitting inside Gi plus 1. This is what you are using. Now, if I say G intersection Gi times Gi plus 1 times Gi by Gi, what is that? Can you identify this part with something using second isomorphism theorem? So it's like AB by B. You remember, this is nothing but A by A intersection B. So this is second isomorphism theorem, which says that it intersection of this by this. So this is where it is important. So this quotient you have to realize like this. This is the important fact. This is important. This is by second isomorphism theorem. This is you agree, right?
Yes.
All right. So now you know this fact. Now, but you have to say something now about this left hand side you have. So this, you have somehow reduced your computation of proving it is abelianness to here. So let's look at this subgroup more carefully, because this has to give some answer. So subgroup is H intersection Gi plus 1. H intersection Gi plus 1 times Gi by Gi. Now, where does this subgroup lie? H intersection Gi plus 1. Where is this contained? Can you tell something about that?
It's contained in H as well as Gi.
It is contained in H as well as Gi. Can I say further it is contained Gi?
Contained in Gi.
Intersection of 2 is always contained in bigger,
Yes.
right? So therefore, this whole thing, can I say it is contained in Gi?
How can you say that H intersection Ga plus 1 is contained in H intersection Ga?
Okay, I think I minus 1 is there. Or sorry, I think this is not the case that we are trying to say. This is, I'm sorry. So H intersection Gi plus 1 is contained in Gi plus 1. This you agree?
Yes.
And Gi is also contained in Gi plus 1. Do you agree?
Yes.
So what about the product? Can you say something about that? Is that contained in Gi plus 1? Because it is group, right? We are talking inside group.
Both are groups.
Right? So this is nothing but this. Can you say this?
Yes.
Using this fact, we can say this. Now, this is isomorphic to what we want, right? H intersection Gi plus 1 by H intersection G. You agree, right?
Yes.
Therefore, this is abelian. Subgroup of abelian is?
Abelian.
So subgroup of abelian is abelian. I mean, this is little bit like the group theory part, but this implies that your H intersection Gi, or I think H is solvable directly. This is okay. The proof is okay, right?
Yes.
All right. Now, homomorphic image of a solvable group is solvable. First, we prove subgroup of a solvable is solvable. Homomorphic image of solvable is solvable. You can use this fact somewhere. Whenever it comes, you can use this fact. So what is the definition of homomorphic image, first of all? What do we mean by homomorphic image? So suppose
Phi is a group homomorphism from one group to another.
Okay.
Which is 1-to-1.
Plus 1 to 1.
Then phi of G is called the homomorphic image of
G. Yes. Homomorphic image of G under phi. All right. Yes, you are correct. So, right. So what we are trying to prove that this phi G is solvable. So phi G is a solvable. Given G is solvable. Because we are trying to prove homomorphic image of solvable group is solvable. That means if G is solvable, its homomorphic image phi G is also solvable. So, in order to prove this, I will try to prove first one thing, that quotient of solvable is solvable. So that will be very easy to prove that homomorphic image is solvable. And that you will tell me why. So let me prove. So in order to prove, we will prove this. Okay, so in order to prove this, so we shall prove quotient of solvable group is solvable, or let's say H is normal subgroup of G and G by H is solvable if G is solvable. This is what we are trying to prove. All right, so let me use the definition that G is solvable. So G is solvable, then we have a chain of subgroup G0 equal to G, trivial contained in G1, contained in Gn equal to G, such that Gi by Gi minus 1 is abelian and Gi minus 1 is normal in Gn. Right, this is the definition for being G solvable. How can we, again, we want to disturb this chain and we want to make a chain which we want for the group G mod H. All right, so can you guess what is that chain?
Take quotient with H throughout.
Okay. Let me write that. So what you are trying to say, take quotient throughout E mod H. Contained in this, you are saying G1 mod H, contained in G mod H. Well, what about this? Is this what we want? No, right? What is the identity element inside G mod H?
The inclusion reversed.
Sorry, inclusions are reversed, yes. Okay. But what is the meaning? I'm somehow trying to say that there is no meaning here, huh? Because our trivial element is this, and therefore this is the trivial element for G mod H. Huh? This is we want. So last element has to be this. Can you modify this? Now I want you to modify this, and you will be able to do it. Huh? Can you modify this group a little bit so that you will get the chain?
H is contained in.
So okay. Let me give you some hint. So H is contained in GIH, right? For all our product is contained, right? How? Let's say, how do you see H inside that? It's like E dot H. You see like that. You should see. So therefore, there is a containment of H inside GIH. And GIH is a subgroup of G. Huh? So this containment we have. Now I have given you some group structure, somehow this is the hint. This should give you some hint that how to see the groups. So if I take, let me do it now. So if we take E, okay. So our chain was nothing but G0, G1, Gn equal to J. I'm writing now this to be G0 H mod H containing G1 H mod H containing G2 H mod H, so on, Gn H mod H. And this is nothing but G mod H. Why? Because your Gn is G and H dot G is G because H is a subgroup of G. If you take product of H dot G, anyway H is contained in whole of G, product will be nothing other than G. So is this, at least the chain is okay right now? This is just the element H, only H element. Why? Because we have E time H mod H. So just this only, a single element inside that. Do you understand this?
Yes.
All right. So now we are trying to prove this is a chain of G mod H, and we are trying to prove that Gi H mod H is normal in Gi plus 1 H mod H, and the quotient Gi plus 1 H mod H, quotient with Gi H mod H is a billion. Which one do you find it's easy to prove? I think one of these properties is easier. Can you see which one?
Maybe the second one.
Second one. Very nice. Why? Because can you use some fact?
Gi plus 1 by Gi is abelian.
Well, that's okay, but how do you realize this whole thing is? Can you see an isomorphism, this group with some known group? Can you use some isomorphism theorem here? Third isomorphism theorem, that A mod C, mod B mod C is isomorphic to A mod B. Can you use that? This should be Gi plus 1 H mod Gi H. This is okay, right?
Yes.
These all ABCs are group. These are not symbols. Groups and subgroups properly, the way they have been. Okay. Now this is all about saying this as abelian when you know that Gi plus 1 by Gi is abelian. Given this, you have to prove this. That's also not very difficult. Why? Because you can define a map from this to that, right? Because Gi plus 1 to Gi and Gi plus 1 H to Gi H, there is a natural map. And what is that natural map? You take any element here, it will look like this, quotient. Some coset, like this, and this will map to which? A times Gi H. Is okay, right?
Yes.
And you can very well prove that this is onto, and this is well-defined homomorphism. And therefore, your, what do I want to say?
Is it 1 to 1?
Is it 1 to 1? I doubt about 1 to 1, but it's onto for sure. I doubt about 1 1. Because once you have cosets, then I doubt about 1 1. But I think that we don't need even. We don't even need. Why? Can you say that we don't need that? Because
subgroup of solvability.
That you have proved now. So therefore, this is easy to say that this is abelian. Yeah, I think you are right. Mm, it has to be 1 and on to both, I guess. Then we can say psi of g. Let's say this is map psi gi mod gi plus 1 is same as gi h mod gi plus 1h. I think I'm reversing the direction. Huh? Gi plus 1 by gi is gi plus 1h mod gi h. Yeah, once you have psi to be bijection, then you know that this is equal. And therefore, if this is abelian, then you know that this is also abelian. Now, abelianness is okay, but normality, we have to also check normality, right? So I think I will leave this part normality to you, or maybe we can discuss in next tutorial. But let me write quickly what do I want to say here. That finally you can prove that gi h mod h is normal in gi plus 1 h mod h using gi is normal in gi plus 1. It's not that very difficult, but you can prove it. And then finally, one can say that G mod H is solvable. So finally, we have proved the quotient is solvable. Our goal is proving homomorphic image is solvable. Till now, we have proved quotient of any solvable group is solvable. But I'm saying homomorphic image is not very difficult. Why? Because phi from G to G prime, your phi G. Can you write this phi G as something known? And then you can use some criteria to prove that this is solvable. Can you use first isomorphism theorem?
Phi g by phi g g over kernel phi.
And kernel phi is a normal subgroup, right?
And g is solvable.
And G is solvable.
So quotient is solvable.
Quotient is solvable. So, and then
Therefore, phi of g is solvable.
exactly. All right. So this is how homomorphic image of solvable, and now I think you can prove the later thing. So let's go to quickly to other questions. So let L1 over Q is the splitting field of x cube minus 2. And L2 over Q is the splitting field of x square minus 3. Simple polynomials. What is the composite of L1, L2 over Q?
The polynomials are same, then it is.
Then it is.
The splitting field you want to prove their product x cube
Yeah.
minus.
So L1, L2, what is the definition of composite? Can you recall that? I think that will answer the question. What is L1, L2?
Forgotten.
Huh?
L1, L2 definition.
Yeah. So composite of two fields. Given two fields, what is the composite of that? Sometimes people composite them, sometimes people. But we will use composite.
Smallest field containing both L1 and L2.
Yes. Smallest field containing both L1 and L2. Very right. Now, can you tell me what is L1, what is L2, and then finally what is L1, L2 for part A? L1 is splitting field. Huh? Can you tell me that?
Yes.
It's easy.
X cube minus 2 is, that is x cube 2 power 1 by 3, 2 power 1 by 3 omega. So it is
Yeah, L1 is
L1 is q of 2 power 1 by 3 comma omega.
or I. If you don't mind, I will take I. Is that okay?
Yes.
Okay. Now what about L2?
L2 x squared minus 3 root 3 comma I.
I. Sure.
Only root 3.
Only root 3. Yeah. So what will you say the composite then?
Is 2 power root 3, 2 power 1 by 3 comma I.
That's it. The smallest field containing all. Okay. Let Fx be an element in Qx and Galois group of F is nothing but A5. Is F reducible or irreducible? Suppose some polynomial has Galois group A5. Is the F reducible for that or irreducible?
Galois F is A5 is not solvable.
A5 is not solvable, of course, that's correct.
So Galois F is not solvable.
Okay, that's okay. So let's try to prove by contradiction. Suppose this polynomial is reducible, then what can go wrong? So let's make this fx is reducible. Then what can go wrong? I can write f to be some g dot h where given the degree of h, what can be the possibility for degree g and h? Yeah.
Less than degree of F.
Less than the degree of, less than or equals to degree of f. And what is the possibility for the degree of f? Can you tell me that? So you know one thing, that degree, your Galois group of f is
Strictly
always
less than or equal to circle.
right. Why? Because so therefore this degree of gi has to be less than equal to 4. Why? Because your degree of f is actually 5. Why? Because your Galois group of f is always less than equal to degree of f factorial. So that means it is your Galois group of f is a subgroup of S5. So if we are working over A5, that means the polynomial has degree 5. So if it has reducible component, degrees of those polynomial has to be less than equals to 4. But does it contradict something? So just if you look carefully, that if some degrees are less than equals to 4 or something, they should tell what is the Galois group of those polynomials, right? If you have degree, then you must know the Galois group also. Can we use that information to say that there is contradiction? So K is the splitting field of F, and
K1 is the splitting field of G, K2 is the splitting field of H, then what can you say about K, K1, K2 and F? So Galois group of K over F, that is given to be have order 60.
Maximum.
Maximum. About this and this, what can you say? They have degree less than equals to 4.
Less than. So 4 and 15.
Is it possible? So suppose your K over F that has at the most degree 24. But the other polynomial, once you have degree G is 4, the degree of H has to be how much? 1 only. Once your degree of your H is 1, then the extension field is also degree 1, right? That means it is reducible, and therefore the degree, there is a issue with degree, right? Such combination is not possible. Do you see some contradiction here?
Here K equal to K1 equal to K2.
Okay, so I think I will just try to show you that once you have F equal to GH, the degree of G and degree of H, either of them, one of them has degree less than equals to 4, another degree has to be 1 only. Once you have degree 4, then there is a issue.
Degree 1
Because,
is,
yeah.
K and K1 are equal. K and K2 are also equal.
Yeah, so somehow this should be the way that 5 should divide Galois group of K over F. Can you say this point? Once you say this, we are done.
So degree of F is 5.
Yes.
Degree of
So if you can convince at this fact, I think then we are done to say that this is not possible. Or maybe either of the way that you see previously, either of the way. You can say that such a thing is not possible. So I think this has been discussed in the class lectures also. Once you have either S5 or A5, either of these facts are there, then your function, your polynomial cannot be reduced. This cannot happen. This has to be reducible. Because once it is reducible, there is an issue with degrees. I think, I mean, some lacking of time. If we will have some more time, maybe we will discuss this part again in more detail. So I will write this question more detail. Let's go to quickly to this part, and I think we will discuss this previous question in the last live session. Okay, so what is the Galois group of the first polynomial? Just let me do this question first. We will come to this. How do you check irreducibility of a polynomial of degree 3? What are the ways?
You can take X common.
So one thing is that whenever you have degree 1, if you want to say it is reducible, then degree of G has to be 1 and degree of H has to be 2. Or degree of G is 2, degree of H is 1. Or it is completely like product of 3 factors. Do you agree that? Either of case, you say that there is always a linear factor. That means there is always a root. Once you, that property that you have, that either of the way you can argue that there is one way Eisenstein criteria. Other way is rational root test. There is one more way. Can you say find that one way? It's mod P. Do you know that?
Yes.
What is that?
Mod T test.
Yeah. So if you can find a root modulo P,
Yes.
then you can find in Q also. And if you don't have any root modulo P, then your polynomial does not have any root, right?
Irreducible.
So therefore, there are several tests to check, and I think I'm not checking, and you can find the Galois group for this. Because for degree 3 polynomial, it always depends on the discriminant. Once your discriminant is square, non-square, it completely determines whether the Galois group is A3 or S3, right? So part B I'm leaving. Part A, let's do part A and then I will stop. What is the Galois group of fx x power 5 minus 9x? I think it's simple. Look at the polynomial, I guess, you will see it.
So you can take x common.
Okay, let's write. So fx is x power 5 minus 9. Take x common, it will be x is 4 minus 9. Can I re-simplify it?
X squared minus root 3, x squared plus root 3.
Just 3, right? Not root 3.
3.
Now can you tell something about a number of real and non-real roots? There is some property about number of non-real roots.
The number of exactly 2 non-real roots.
There are exactly 2. What are those? Namely,
root 3 I, root 3 minus I.
wait. 3i minus root 3i. Alright. So, of course, these are the roots which are not. Now, do you know some result about some theory when you have exactly 2 real roots?
So the Galois group of F is S5.
Then Galois group of F is S5. Exactly right. Galois group of F is S5 when you have degree 5 polynomial. Yes. So, okay, then you know, I think results most of the things you know. If we have 2 more minutes, then let's do. Let me not do this question because this is also depending on discriminant. So use formulas of discriminant and resolvent kernel. Sorry, resolvent cubic, and then describe the group. That you can do, right? Because these are degree 4 and there are specific type of these polynomials. We know how to find discriminant and resolvent cubic, and then you can tell the group, right?
Yes.
Okay, so I'm leaving this part. Now let's go to this part. So there is one beautiful result about that. If you know, we have definition of solvability of a polynomial says that roots are solvable. Then only polynomial is solvable, and all the roots in fact. But for an irreducible polynomial, question says why for an irreducible polynomial only one single root is enough to say that it is solvable or not. Can you see that?
So you mean we did not check all roots, just only one root?
Yeah. So for irreducible, the question says that it is enough to check single root whether that is solvable or not. Once you have one root is solvable, then you don't need to check others, provided your polynomial is irreducible. So let's write that one root. Let's say alpha is solvable. It is one root. Okay, one root of f. Definition of solvability of a root, what do you say? There exists tower of extensions, right? There exists some tower of extension L1 contained in L2 contained in LR where this alpha lies, and this L over F is a radical extension. You agree, right? and this final field has alpha as an element. This is definition of solvability by radicals, right? Now we are trying to say that this is enough. Why? Because if you remember one result, given a radical extension, you can always get a bigger extension, let's say K, containing your L, such that K over F is not just radical, but it is a Galois extension. Do you agree that? Hello?
Yes.
So once you have this, is it like, do we really need to check all the roots, or this is okay, this is done now? So why? Because your alpha is in L, L is contained in K, and what is the definition of K?
K is the splitting field of F.
K is a splitting field. So that means all the roots lies in K. And there is
Yes.
one more property about K, the extension. What is that? The radical extension. So whenever we are trying to find the roots in a radical extension, we say that that element itself is solvable by radicals. You agree, right? That means all alpha i's, the roots, are in K over F, but this is nothing but a radical extension. And by definition of solvability by radicals, alpha i's are solvable. So the good part is about this happens that you are writing this fact, no, just because your F is irreducible. This you can do only for that. Okay, so I think this is done. So just because we have written L is a splitting, K is a splitting field, and F is irreducible, this is how we got this result. So irreducibility is important here. All right, I think this is the last question, and we will discuss, I think, from this part, inverse Galois problem, and from all these things we will discuss in the last tutorial. And one more thing, in the last tutorial, so I have made an additional 1 hour session so that I will recall from the day one things to the day last day things, small results and some examples, just to recall the whole theory in one single day, and that is on next Sunday, and from 6 to 7, I guess. So classes, this last tutorial is from 3 to 5, and this additional session is from 6 to 7.
Oh.
Yeah, okay then. Yeah, thank you. I will stop here. Yeah, let me stop the recording.